All right, so let's check out some of this bookwork from section 2.3. So this starts on page 176. Okay, so this is taking the place of what we're doing would normally do in class together. Okay, but before you do this, if you haven't done so already, make sure you probably want to watch that introductory video on this. Okay, so again, that introductory video kind of get the idea down first, and I think especially with this one, you really want to watch that video first before you start jumping into this stuff. Okay. But one of them, so like I said, if you haven't watched that first, stop this video right now. Watch this one first. That the one that's on D2L under the content tab for the pre-section videos, right? So watch that first. And one of the biggest punchlines to that, if you did, well, hopefully if you're continuing to listen to me now, then you already watched that video, was these basic exponent rules. And it went through a lot of different examples of how these exponent rules work. Okay. But what the book work, what we want to talk about now, is kind of using these ideas. Okay, so we'll kind of talk about them as we go through here. Okay, so let's check out this Explorer for starters. All right, so with this Explorer, you got, let me see if I can zoom in there on this. You got Anna, she's making brownies and debating between an 8-inch round pan or an 8-inch square pan. Okay, so she's got these two pans, she's not sure how to do this, right? Or which one to use. And if Anna likes thick brownies, which pan should she use? Explain why and use an appropriate calculation to support your answer. And then later we'll do the part B. But think about, right, so think about with this Explorer here, what are we talking about here? Okay, she's making brownies, right? So she throws the brownie mix in and the milk and the eggs and flour, whatever it is that she's using to make it, but she mixes it all up in this giant batter. It's in this bowl, right? Then she's going to take the mixture that's all ready to bake and pour it into a pan. Okay. The question is, should she pour it into an 8-inch round pan or should she put it in an 8-inch square pan? Right. So what we're talking about is we have something that is either a round pan or a square pan. Okay. So when they say an 8-inch round pan, what they're talking about there is all the way across going through the center, right? So this is 8 inches all the way across. Okay. Or a square pan is talking about 8 inches on a side. Okay. So it's 8x8 square pan. Okay. So for part A, Anna likes thick brownies. Which pan should she use? So, okay, so think about what we want to accomplish here. So imagine she's going to take this batter and pour it into this pan, right? And the batter is going to spread out over the circular pan, or she's going to pour it into the square pan, and again, the batter is going to spread out. Okay, but think about. So this is what I'm talking about. Is like you're looking down on the pan, but three-dimensionally. See if I can try to draw this. Right, the pan, it's more of a cylinder looking thing, and so this is like the bottom of the pan, so she's going to pour it in there, or right, she's got this square pan, so this is kind of like looking at the base of it. Okay, so think about what we want to have happen. If she takes the mixture and spills it into here, or pours it into here, or pours it into here, okay, it's going to spread out across the bottom. Okay, but if she wants to have thicker brownies, then we want it to be higher, right? So we're trying to know which one would be thicker. So which one would be higher? Well, what would cause that to happen is if it spreads out more at the bottom, then there's less to go higher, right? So if the batter would just spread out more over this square pan, say, I don't know yet, but say it spread out more than over the circular pan, then there'll be less to cause thickness, or vice versa. Maybe it spreads out more here, there'll be less to have thickness. So what we need to know is how much is it going to spread out? Or imagine filling this pan up, it's going to spread out over the bottom or spread out over the bottom. So what are we looking for? We want the area. And that's what we're trying to build to is, yeah, we're trying to get to exponent rules too, but it's just using these things as well, okay? And more specifically, also the units, which is really key here. Okay, we'll get to that in a minute. But basically what I want to know is the area, okay? I think this one here is a little bit easier to calculate the area of. So here, remember, area is basically length times width, right? Or in this case, I want to make sure I stress this because yes, everyone goes, oh, it's 8 times 8 is 64. True, but more specifically, it's not just 8, but it's 8 inches. And then you're multiplying the width, which is also 8 inches, okay? So really want to make sure you stress the units here. It's not just 8 inches. It's not just 8, it's 8 inches. so that when you actually do that multiplication, yes, 8 times 8 is 64, but the larger point here is also the inches times inches. Oh, okay. So there, you're talking about those exponent rules which we're talking about in that other video, the introductory video here. So if you're talking about inches times inches, you're multiplying things with the same base, you would add the powers, right? Or inches times inches, this is like power of 1, this is power of 1. So this would be inches squared, right? Or that's where you talk about square inches because it's inch times inch or square inches. That's where the name comes from because it's coming from a square. And that's why the abbreviation of, when you say inch raised or a unit raised to the second power, you can say inches squared, for example, because it comes from a square. All right, so anyway, what is the area of that pan? Would be 64 inches squared. Okay, but now over here we're talking about a circle. Well, it's a little bit more complicated to it, but hopefully you've seen that before at some point, right? There's a bunch of formulas here. You don't have to memorize these. We'll talk about these in a minute. But one of the things we definitely can do is we can find the area of a circle, if you remember, is pi times the radius squared, or the area is pi times the radius squared, or pi r squared for this one. But remember, the radius is the distance from the center to an edge, or to the edge of the pan in this case. So this would be r. But they told me my pan was 8 inches. So if it's 8 inches all the way across, that means the radius here would only be 4 inches. Again, not just 4, but 4 inches. So now the area of this pan, or the base of the pan, would be pi times the radius squared. But here we're talking about 4 inches. Okay, which means this squared is not only acting on the 4, but it's also acting on the inches, right? So this is pi. 4 squared means 4 times 4, right? 4 times itself would be 16, and the inch is squared, right? Because the squared is acting on the inches. And then you can just throw that in a calculator or whatever, right? You can use the 3.14 for pi if you like, right? So what I'm saying is you can do the pi, which is the, approximating with 3.14, right? 3.14 for pi and then multiply by 16. So you're going to get 50.24 inches squared. All right, so now, if the base of this pan covers 50.24 inches squared, or that's how much stuff would be, over here, the base of this pan is 64 inches squared. So here you can see, hopefully, that the base is larger on this one than it is this one, right? This one's a larger area, right? I mean, 64 inches squared is larger or greater than 50.24 inches squared. So that means the batter is going to spread out more here. So if it spreads out more here because it's a larger area at the bottom, the batter is not going to be as high then here. It would be a lot higher here because it's not spreading out as far. So if she's looking for thick brownies, she should go with the circle pan, right? Because the base covers less area. It's basically okay. So it's one is using that concept, but it also is getting used to the units, especially with the exponent stuff. Okay. But what about B here? If Anna wants to as much crispy edge as possible, which pan should she use? So now she wants as much crispy edge. So with this is A, B. But now with the edging, so here, let me draw the picture again. Okay. So now instead of the base being what we're talking about, we want to talk about the edging, right? So we're talking about the edging here, or we're talking about the edging around it, right? Not the bottom, but the sides, basically. Okay. Or the sides of it, if I, take the pan and look at it, look down on it, basically, what are we talking about? You are talking about the distance around the pan, right? Or if I take this pan and look down upon it, it's going to look like that square. But what we want to know is around it, right? So if there's more stuff around it here, or if there's more stuff around it here, whichever one has more stuff on the outside, then that would give us more crispy edging, right? So we want more edging, basically, more outside. Or in this case, instead of area, we're talking about perimeter, Okay, so in this case, the perimeter, you could literally just add them all up, right? So it's 8 inches for one side, plus another 8 inches, plus another 8 inches, plus another 8 inches, right? You can add all 4 of these up. But again, the key here is it's not just 8. It's 8 of these inches, plus another 8 of those same inches, plus another 8 of those same inches, plus an 8 of those same inches. So the thing of it is, these are all like each other. Oh, they're all inches. So 8 of these things plus 8 of those same things plus 8 of those same things, right? You got 8 plus 8 plus 8 plus 8. So there's your 24. But again, it's 24 what? Inches. Big difference here. Like, see here, you are multiplying inch times inch gives you inch squared. Here, you are not multiplying the inches. You're adding up 8 of these things, right? And if I gave you $8 and add $8 and add $8 and $8, you'd have 24 of those dollars, right? Or if I gave you 8 apples, 8 apples, 8 apples, 8 apples, you'd have 24 of those apples. It's the same thing here. It's just that they're inches, right? But then over here, for whatever rhyme or reason, quirk of history, when you're talking about the perimeter of a circle, it's got its own name. It's called the circumference, right? So if you're talking about a circle, the circumference of a circle is this 2 pi r, or it's twice pi times the radius, right? But it's the same thing. It's just perimeter. It's the distance around the circle, okay? But it's the same thing. You can take the 2, the pi, and then multiply by the radius, which again, in this case, is the 4 inches. So number-wise, you've got 2, you got pi, you got 4, so you can throw those all together in the calculator, right? You got 2, then you can multiply by the 3.14 for the decimal approximation of pi times 4. So 25.12. So this would be 25.12 of those inches, right? So the distance on the outside of this pan would be 25.12 inches. The distance on the outside of this pan is only 24 inches. So the 25.12 inches is greater than the 24 inches. Again, that's the one you'd want then. Right? Okay. So the key there is using the units correctly as well, not just the knowing how the numbers and then applying it. Also, there's all kinds of formulas. Like if you look on the sheet here, it's probably easier to see on yours, but there's formulas for areas, rectangles, parallelograms, trapezoids, all this good stuff here. Do you have to memorize these? No, by no means. Okay. What's more beneficial here is using them, and especially using them in the larger context of knowing how the exponent rules work. Okay. So we'll talk more about these as we go through. But one thing I do want to mention, it's things like, you got the circle, right? Whenever you talk about a cylinder, right? This is a cylinder, right? And then the letters you kind of context clues, right? So if they're talking about the V here, talking about the volume, or here the S, they're talking about the surface area, right? H is the height. R is the radius of these. We'll get to these more, right? But that's the point they're trying to make with number 2 here is when you see common lettering, you kind of have context clues and common things like A for area, V for volume, S for surface area, H for height, B for the base, L for the length, things like that with smaller base, radius, diameter, height, right? Just by seeing those letters, you kind of got to associate it with it, what you're talking about. Not a big deal, okay? What's way more important here is, we'll come back to that using the stuff in the area formulas and volumes and whatnot, is these exponent rules. Okay, this is what we're trying to get to. Okay, I'm going to leave this, let you guys do this on your own. But hopefully, like I said, if you watched the video of what the pre one to this should be easy, right? But ultimately, what we're trying to get to, if you watch that video from the pre-section stuff, is this punchline right here, these exponent rules, okay? Right. So the major things that we're trying to get used to here is if you're multiplying things with the same base, you would add the powers, okay? Division means subtraction. Something raised to a power raised to another power, you would multiply them, right? And if you have, as long as you have multiplication or division inside of a power like this, you can bring the power to each one. And then one, this is one you just might want to stick in your memory bank, but just about anything raised to 0 is 1. Okay. Again, did a bunch of examples in that pre-video. Watch that, please, if you haven't done so. All right, but let's check this out. So the actual work here would be, like number 4 is really what we want to talk about here. So let me talk about these. What I would highly recommend, if you're watching this video right now, pause the video. try these on your own. Okay. So seriously, like if you haven't done so already, pause the video, try these on your own, and then we'll talk about them. Right. But you got to be able to do them on your own first. Okay. Or at least attempt to. So with these, we want to simplify. So there's a couple different ways you can think about this one. Okay. The short version of it is, since you're multiplying all of these things together, right? You can, let's put the numbers together first, and then we'll do the variable part. Okay. So what I mean by that is you can do the number part first, right? 17 times 2 would give you the 34. And then since you're multiplying here, you can just add the powers. 2 plus 5 would be 7 of those x's. Done. Right? But just quickly, just so you see, I think it might help to go through the long version of what's really happening here. Remember, this is saying 17, and then you're multiplying by x squared. But what does x squared mean, right? This squared is acting on the x, or in other words, that's x times itself, right? Think of it as this thing, this number times itself. Then we're multiplying by another 2, and this 5 is acting on the x, or in other words, there are 1, 2, 3, 4 of those x's multiplying by each other. Okay. And the point here is now, since you have multiplication, all these, a bunch of multiplication here, you can multiply in any order you want. So to make things easier, the 17, I know what number that is. The 2, I know what number that is. This x, don't know. This x, don't know. And this 1, 2, 3, 4, 5 of them, right? I just basically reordered it so that I could then put the 17 times 2, there's your 34. And then you can see, okay, you really have 1, 2, 3, 4, 5, 6, 7 of them. So since I don't know what x is, what is x times x? I don't know. What is x times that times x times x? I don't know. But I do know there's 7 of them, so I can replace it with x to the 7th, because that's what it means. So when in doubt, you can always just sit there and list the whole thing out and then basically regroup it. Or you could do the shortcuts, right? The same with b, kind of. So the short version is, okay, this 4, first off, this power 4 is acting only on the x. This 2, however, since there's parentheses, it's not only acting on the 4, it's acting on this, right? So really, this would be the same as 4 squared, or think of it as almost like 4 squared, and then you have x to the 4 squared. Now, you can just do it if you want, but I'm just saying the squared is acting on the 4, but then it's also acting on x to the 4. But then from there, 4 squared means not 4 times 2 is 8. Don't do that. Remember, it's 4 times itself this many times, or just 2 of them. So 4 times 4 is 16, right? And then here, this is x to the 4 squared. Now you're taking something raised to a power, raised to another power, so you would multiply. 4 times 2 is 8. So we got 16x to the 8. And I think probably the biggest problem with these problems, when you get used to it, are not hard. They aren't. There's not even that much to do. You can do them really fast. The biggest problem with these is you try to memorize the rules and you got it all screwed up when you memorized them incorrectly, right? So here we multiply. Here when you were multiplying, you added the powers, but here you multiply the powers. How do I know which one to do? Instead of memorizing it, like I said, think about it. What does x squared mean? What does x to the 5th mean? Just look at it. There are 7 of them, right? Here, what does something raised to a power, raised to another power mean, right? So what I'm saying is, think of it as this thing is being squared, which means we're having this thing, which is x to the 4th, but there are 2 of them, right? There's 2 of these x to the 4th. 1, 2 of them. But what does x to the 4th by itself mean? 1, 2, 3, 4 of them. What does x to the 4th by itself mean? 1, 2, 3, 4 of them. Now look at it. Oh, look, there's 1, 2, 3, 4, 5, 6, 7, 8 of them. But see, if you do it this way, no, I didn't say add, I didn't say multiply, I didn't say any of that. I just thought about it. What does the power of 2 mean? Oh, 2 of them. What does the power of 4 mean? 4. What does the power of 4 mean? 4. Look at it. Oh, 8 of them. Done. I don't have to memorize, should I multiply, should I add, right? Think about it. Or memorize it and then check it, right? That kind of thing. Okay, what about C? All right, so kind of the same idea. You want to think of it as this power of 3 is acting only on the x, not the 5 or the negative. But this 2 is acting on all of it. And especially when you have a negative number, you probably don't want to think of this as negative 5. Think of it as negative 5. right? So it's almost like two different things. So what I mean by that is, think of it as you're going to take the negative, square it. You're going to take the 5, square it. You're going to take the x to the third, you're going to square it. So that 2 is acting on the negative, it's acting on the 5, and it's acting on the x cubed, right? So now a negative squared, that's a negative times a negative, that's going to turn to a positive. 5 squared is 5 times 5 is 25. And again, if you need to think this, there's 2 of these. So that means there's an x cubed and another x cubed. Well, there's 3 here and 3 here. That's 6 altogether. Right? Again, if you need to think of it as x cubed, x cubed. Oh, but this is 1, 2, 3 of them. 1, 2, 3 of them. Sure enough, there are 6 altogether. Or something raised to a power, raised to a power. You multiply the powers. 3 times 2 is 6. So, and it's positive. So you really don't need to write that. It's up to you. So ultimately 25x to the 6. All right. Then hopefully you've noticed when you do these that D and E are very similar, but they are different. Okay, so the key here is you have to realize what these things are acting on. What I mean by that is, remember, exponents work only on the things to the left. It's kind of what I was talking about here. When you see -5, don't think of -5 as one number. It's negative and then also a 5. It's the same thing here. Like this, the difference between these two is this 0 here is acting on the 8 only, and the negative's just sitting there, right? Whereas here, the 0 is acting on all of it, because the parentheses says act on all of it, okay? And if you remember, just about anything raised to the 0 power is 1. So this 0 acting on the negative turns it to 1. The 0 acting on the 8 turns it to the 1. The difference here is this 8 to the 0 is 1, but the negative is just sitting there doing nothing because there's nothing acting on it, right? So anything, just about anything raised to 0 power is 1, but since the 0 is acting on all of it turns to 1. Here, the 0 is acting only on the 8. That turns to 1, but the negative just sits there and does nothing, right? So watch out for that. All right, then F goes to 3 on top. This is one of those where it was really nice if we're actually in class. We could talk about these together. Kind of go with what you guys see, because there's many different ways to do this. You got to go with what you see. Okay, I think the most straightforward way, it's long, but you can realize that. Okay, so first off, this power of 4 is acting only on the x, right? It's not acting on the 3, right? It's acting only on this 4. This power of 3 is acting on the y only, or no, it's an x. What am I doing? They're both x. Or whatever. This 3 is acting only on the x, not the 6. But this 2, oh, look, it's on the parentheses. So that means it's acting on everything. So what that means is this 2 is not only acting on the 3, it's acting on the x to the 4th. It's acting on the 6, it's acting on the x cubed, right? It's got to bring it to each one of those. So one way to do this is you could do 3 with that power of 2 on it. The x to the 4 by itself with the power of 2. Then the 6 with the power of 2. Then the x cubed all by itself to a power of 2. Right? Basically just bring the 2 to each piece. And you can go through and compute. Okay, so 3 squared is 9. Here you have 2 of these, right? But each one has 4, right? So there's like, you can visualize 4 x's, but there's 2 of them. So 4 of them and another 4 will give you 8 altogether. 6 squared is 36. 2 of these x cubed. So x cubed and another x cubed. So that's 6 altogether. All right, then you want to try to simplify this. Well, again, I don't know what it is about fractions, but people just do weird stuff with fractions. I'm not sure why, but this is very similar to what we're doing at the very beginning. What I mean by that is, think of it as, there's like, whoa, we're trying to multiply this times this, right? This has a number and an x part. This has a number and x part, right? Number, x part, number, x part. What did we do? We put the no number parts together, and then we put the x's together. You can do the same thing here. Number, x part, number, x part. So it's this whole thing, which has a known number and an x part. And the bottom, this whole thing is a number and an x part. But to make things easier, what you can do is just, let's do the number part together first, and then we'll do the x part later. Okay, so 9 over 36, which then, 36 divided by 9 is 4. Yeah, kind of, but you got to watch what you're doing. Look, 36 is bigger, so there's going to be more stuff left on the bottom. right? This is not 36 divided by 9. It's 9 divided by 36. Or it's kind of like you're reducing, right? 9 goes into 9 once, if you like, and 9 goes into 36 4 times. So it's more like 1/4, right? Okay. Now, as far as the x's are concerned, when you are dividing, you would subtract the powers. Again, you can memorize that, or just think about it. What does x to the 8th mean? It means 1, 2, 3, 4, 5, 6, 7, 8 of them. And on the bottom, what does x to the 6th mean? 1, 2, 3, 4, 5, 6 of them, right? So what's going to happen? 6 on the bottom are going to kill 6 on the top. So you're only left with 2 of them, or x squared, right? X times x would be 2 of those x's. So yes, you could subtract, or when you go to this, you can kind of just visualize in your head, oh, look, 6 of these are going to cancel, since you're dividing, 6 of these with only 2 left. And there you go. Quick side note to this. Go back. That's what most people like to do. They just bring the 2 to everything. Great. Well, another way, if you go back to the original problem, another way to do this one is, since this 2 is acting on the whole thing, what it might be easier to do is, let's simplify the inside first, and then we'll worry about that power of 2 later. So what I'm saying is that power of 2 is still going to be there, but we'll do it later. Let's do what's inside by itself. Oh, we can do that same trick, right? 3 divided by 6. You can reduce it by 3. 3 goes into 3 once. 3 goes into 6 twice. And do the same thing here. 3 of these x's are going to cancel 3 of these x's. So you're only left with 1 of them, right? Or subtract 4 minus 3 is 1. Okay. So then now we can bring this power of 2 to each of these pieces. Or you can even think of it as on the 2 if you like, right? But you're looking at 1 squared, x squared, and on the bottom 2 squared, right? So you're squaring the 1, you're squaring the x, and you're squaring the 2. Well, 1 squared is 1, and on the bottom 2 squared is 4, and you've got an x squared, right? Oh, look, same answer that we got doing it the other way. So this one here, you could, that 2 on the outside, just bring it to everybody and then simplify it, or simplify the inside first. Doesn't matter. Okay. All right, let's check out G then. All right, so we had 3xy squared over the 3y cubed. Big difference. It's probably easy to see on here. Like, make sure you see the difference between these two. The one we just did, see how the whole thing has the power of 2 on it because of the big parentheses on the whole thing. So that power of 2 is acting on everything, so we can bring it to everything, right? Over here now, though, wait a minute. That power of 2 that's on the outside here is only acting on the top, not the bottom, right? So this problem is definitely being separated. I guess I'm saying is you can't simplify these first because that power of 2 is acting on the stuff on the top, not the bottom. So this one, you have to bring this 2 to each piece, the 3, the x, the y squared. Or this is 3 squared, x squared, y squared, squared. Then the bottom is just 3y cubed, right? I'm not doing anything with the bottom. But now each one of these pieces I can simplify. So 3 squared, 3 times 3 is 9. You got x squared. And then here, this is 2 of those y squareds, right? Or, think of it in your head as there's 2 of those y squareds, 1 of them, 2 of them. But this means 2, this means 2. So there's really 4 altogether, right? Okay, now we do the same thing. You can think of it as number part, the x part, but there are no other x's. So that the x squared is going to come along for the ride. And then we can put the y's together, right? So the no number part and the y part, we can put those together. Right, so number-wise, 9 divided by 3 is just 3. The x squared is just sitting there because there's no other x. But here, right, the y cubed and the y to the fourth, 3 of these y's are going to get rid of 3 of these y's. So you're only left with 1. And whenever you have a power of 1, you don't need to write the 1. You can if you want to, but it's kind of implied when you say that, right? I mean, no one says, I have 4 to the $1. No, you just have $4, right? Okay, but there you go. And then the last one here is h. All right, so again, you've got this all times this. But this big power of 2 here, now these parentheses are here. So what that's saying is this 2 is acting on all the stuff that's inside this parentheses, but not this stuff over here. Okay, so you probably want to do that part first and think of it as, okay, this 2, it's got to act on each one of these. So 4 squared, then you're going to have x squared squared. Then you're going to have a y squared squared. And then you're going to have the z squared. Right? This is bringing the 2 to each one of these. So 4 squared would be 16. 2 groups of x squared. That's, x squared, 2 of them. So it's 4 altogether. Same thing here. 2 groups of these y squareds. So it'll be 4 of those all together. And then there's only the z squared. All right, so that's that part. But again, now we didn't do any of this stuff here. Okay. So really what this is saying is you have it's 8xyz times the 16x to the fourth y to the fourth z squared. But it's this 8 times this, times this, times this, times this, times this, 4 of them, times this, 4 of them, times this, but 2 of them, right? But the nice thing about multiplication is you can put any order you want. So what I'm saying is we can multiply the known numbers part together. We can then put the x's together. You can then put the y's together, and then we can put the z's together, right? So first off, the known number part, we have 8 times 16. You can use a calculator if you need. So 8 times 16, 128. All right. Now here, this is x to the 1, so it's 1 of them here. There's 4 more here. So if I have 1 of them here and I put 4 more next to it, then you have 5 altogether. But again, notice I didn't say add or multiply. Yes, that's what you're doing. That's the biggest problem with this stuff is people look at this, oh, it's 1. Am I supposed to multiply here? Am I supposed to add? I don't know. Think about it. 1x, 4 more. Oh, that's 5 altogether, right? Look, I figured out the answer without using the word adding. Just what does it mean? Same thing here. 1 of them here, y-wise. There's 1 here, 4 here, so there's 5 altogether. 1 here, 2 z's here, so 3 altogether. And then we have all my known numbers together, x's together, y's together, z together. So you're done. And there you go. Okay. This is where the homework is really going to come into play because you got to just practice these. It's the best way. Okay. One and the other issues is not only applying these rules, but then let's go back and use it. So like with 5 here, they want you to find the area of a triangle whose base is 5 inches and height is 20 inches. And here's probably the biggest thing that I think most people forget to do is include units in your work, meaning not just your answer, but it should be in your work, right? And that's what they're really trying to get to here, right? And that's why it's combining those where we started with that, all these crazy formulas and then the exponent rules, okay? But first of all, we want to find the area of a triangle, okay? Maybe I should draw the picture. We're talking about triangles. Let's draw a triangle whose base is 5 inches and the height is 20, right? So it tells me the base is 5 inches and the height is 20. And I want to find the area. Okay, so how do you find the area of a triangle? Well, one you might want to know, it doesn't really matter. But anytime you're talking about a triangle, it's going to be the area, it's going to be 1/2 base times the height. Which, if you think about it, the reason for that is if I were to take a rectangle, length times width, if I take a rectangle, which is length times width or base times height, whatever you want to call it, but multiply these together, what is a triangle? It's half of that, right? So that's why the area of a triangle is 1/2 base times height. Okay, but here's the thing. It's going to be 1/2, but not times 20 and then 5. What I'm saying is it's going to be 20 inches. And then we're going to multiply that by 5 inches. Okay. This is kind of like the 20x and the 5x, right? So think of it as kind of like the known numbers you're talking about here, just like we were doing, the known numbers. But the units are kind of like your variables. They're not varying, but they're going to behave like that, right? Or in other words, what I'm saying is we can put the numbers together first, the known numbers, right? Multiply 1/2 times 20 times 5. 1/2 of 20 is 10. 10 times 5 is 50. But the point here is now, what is inches times inches? There's 1 of them here, 1 of them here. So there's 2 all together. So it's really 50 inches squared, right? So yeah, it's not just using the formula, oh, it's a half times 20 times 5 is 50, sure, but it's also using units, which is really the larger point of why we're talking about it now. Okay, let's talk about B. So I want to find the volume of a cylinder whose radius is 2 centimeters and height is 1 centimeter. Find an approximate answer by using 3.1 for pi and round to the nearest tenth. But again, include units in your work. Okay. So talking about a cylinder here. So a cylinder is kind of like a can. And they told me that the radius is 2 centimeters. So if I went from the center of the can to the edge of it, that's 2 centimeters. And they told me the height is 1 centimeter. Right. So the radius was 2 centimeters and the height was 1. Okay. So what I want to do is I want to find the volume of it. It's not a big deal where this comes from because you can just go look this up, right? But the volume of is how much stuff is in here. But if you think about it, it's just the base, which is the pi r squared. You can kind of see it in there. See, the volume is this pi r squared h, but the base is just the area, right? About pi r squared. Talking about that from a circle, basically. But imagine stacking up a bunch of circles, right? So stacking up a bunch of circles would cover your h. So you're taking that area of the base, pi r squared, and multiplying it by how many it would take to stack it, so h. Or your volume is the pi times r squared times h. Right? So in this case, it would be pi times the radius squared times the height. But again, what's the radius? It's not just 2. It's 2 centimeters, right? The height, it's not just 1, but it's 1 centimeter, right? So this is what they say when they say units in your work, is you're actually going to use them. Or when you go to compute this, right, or simplify it, think of them as kind of like your x's or your variables, right? So meaning like this 2 is going to act on both of these. So that pi is just sitting there, sure. But then you're going to have a 2 squared. Then you're going to have the centimeter squared, right? Because that square is acting on the 2, but it's also acting on the centimeter. And then here you're multiplying by 1, and then you're multiplying by another centimeter. But we can do the same trick we've been doing with the other ones, right? Put the numbered parts together first, and then we'll go back and do the units, right? So number-wise, you got pi times 2 squared times 1. Well, 2 squared is 4. So basically, this is 4 times 1, which is 4, times pi. So you could do the 4 times the 3.14. So number-wise, no number out front, you're going to have the 12.56. But now there's 2 of these centimeters. There's 1 of these here. So when I multiply these together, remember, you're going to add the powers, or 2 plus 1 is 3. So this should really be centimeters cubed, right? It's kind of like an x squared and an x, 2 x's, 1 x is really 3 of them all together. They just happen to be centimeters now. But there you go. So your volume would be 12.56 centimeters cubed, right? Okay. Then the last one like that. For C, for a sphere, I want to find the ratio of its volume to its surface area. Okay, so there's kind of a lot going on here, but it's okay. So first of all, we're talking about sphere, which what it looks like there, a sphere. But find the ratio. So stop. Ratio, same as it was before. It means a comparison, it means a division. We're taking something and divided by something else, right? But I want to compare the volume to its surface area. So think ratio, division, fraction. What am I dividing? The volume to its surface area, right? So trying to find the ratio of the volume compared to surface area. Okay. Well, which sphere are they talking about? They didn't tell me, so it could be any sphere. But if I go back and look on my little chart here, I'm talking about a sphere. It's like a ball. It's a three-dimensional object, right? So the volume, no matter what the radius is, it's going to be 4/3 pi r to the third, right? So the volume is going to be 4/3 times pi times the radius to the third power. And no matter what it looks like, the surface area is going to be 4 pi r squared. So you're going to have 4 pi r squared, right? So for any sphere, that's what the volume is going to be. For any sphere, that's the surface what it's going to be. What they want to know is what the ratio is. So we're comparing these. So now we're right back to kind of what we were doing before, where you were dividing out all, using these exponent rules. But it's kind of the same thing. You can put the known number part together. You can even put the pi part together, and then you can do the r's later, right? So first thing, you've got this, which I don't know, once you get used to, you can hopefully see the fours are going to cancel. So basically, you're just left with 1/3, right? Or 4 divided by 4 is 1. Here, the pi's cancel completely, or you could subtract the powers, right? It's power of 1, it's power of 1. 1 minus 1 is 0, which means it's gone, okay? And then here, this is r, right? But if you have 3 of them on top and 2 of them on the bottom, 2 on the bottom, we're going to cancel 2 on the top, so you're only left with 1. So there you go. Or basically what this is saying is no matter what the sphere looks like, whatever, however, if it's this big or this big or this big, whatever, if I take its volume and compare it to its surface area, right, the volume is going to be basically 1/3 of the radius in comparison to the surface area, right? All right, so it's kind of just combining the ideas. Yeah, you can check out 6. It's basically what I was just saying earlier, but I do want to make sure that we do get to this idea. And we'll talk a lot more about this later. We'll do a lot more examples of this. But the fractional exponents can be weird, right? But basically what fractional exponents are all about are raising it to crazy looking fractions. But the key is you just have to translate it to a root or a radical, right? Like a square root or a cube root, which you're used to. Okay, so what I mean by that is, I guess the biggest thing is, just as an example here, just to show you, to get the blood flowing before we get to that. Like if I gave you something like, I don't know, 5, no, it's not 5, we'll be there all day. If I gave you 16 squared as opposed to 16 to the 1/2, okay? So there's a big difference here. So if you're talking about a number raised to a normal power that, a nice number that you're used to, what does that mean? It means you take that number and you multiply it by itself that many times, okay? Or kind of what you want to do is you want to think of it as you're starting with this 16, and where am I going with this? The end, I don't know, okay? So think of it as you're starting with 16 and you're going to do something with it. So you're going to take 16 and multiply by itself twice, right? Or there's 2 of them, so 256. Okay. Now, when you see a fractional power, think the difference here is you don't know where you're starting, but I do know I want to end at 16. Or what this is saying, in essence, is, see, the difference here is you're starting with this number, and you're going to multiply that number. I'm going to use this number to end somewhere else, okay? When you see a fractional power like this, think, I don't know where I'm starting, but I know where I want to end. So see that the denominator of 2, so what this is saying is there's some number out there, so I multiply by itself gives me 16, which in this case would be 4, right? 4 times 4 is 16. So 16 to the 1/2 would really be 4, right? Okay, so let's check this out. Well, let me just, you can come on here, but there's just a bunch of problems where they want to evaluate each of the following, check your answers, you can use a calculator on these as well. So if I gave you like 64 to the 1/3, B, I'm just writing them all down so I can see. Negative 64 to the 1/3. C is 16 to the 1/4. And D is 144 to the 1/2. Okay. So basically think, okay, we're kind of looking at these all together. The denominator here is a 3. So think I'm doing something 3 times, 4 times, twice. Okay. The difference between these fractional powers and normal regular powers that you're used to is, don't think of it as you're starting at 64. Think of it as you're starting somewhere else, and I want to end at 64. Or since it's a fractional, think of it as I want to start with something and multiply by itself 3 times to end at 64, right? Which we'll get to in a minute. But it's kind of the same thing here. Think of it as, again, it's a 3, so that means I'm doing something multiplying by itself 3 times, but now I want to end at negative 64, right? See, this one is, it's a 4, but it's in the denominator, so that means I'm doing something 4 times to end at 16, right? 2 times to end at 144. Right? But whenever you see a fractional power, think, I don't know what number I'm working with, but I know where I want to end at it. And now you just gotta, most of these you just gotta think, what number times itself is gonna get you to 64? Well, worst case scenario, you can just keep trying stuff, right? So 2 times 2 times 2, right? 3 of them, it's gonna give you 8. So that's not it. 3 times 3 times 3, 27. That's not it. 4 times 4 times 4. Oh, 64. So that number that you keep multiplying by itself is 4. That's why your answer here would be 4. Right? And then what they were talking about on the calculator is you can actually type it in 64 and then like the raise to the problem here is you want all of the 1/3 to be up in that power. So we got to make sure you put in parentheses. But if you did 64 raised to the 1/3 power, but you see the 1/3 all in parentheses, sure enough, it gives you 4, right? But this is what's really happening. So it's kind of the same thing here, but I want 3 things to multiply to negative 64. Well, that would work as long as you had negative 4s, right? I mean, negative 4 times negative 4 times negative 4, right? Or think of it as the 4 times 4 times 4 size-wise is still going to be 64. But negative times a negative is positive. Positive times a negative, oh, I am indeed in a negative 64, right? So this would give you negative 4. One thing, you can type this in the calculator, but you'd have to do it as well in parentheses. So you have the parentheses, negative 64, close, raised to, then another parentheses for the power, right? So the base has to be in parentheses and the power has to be in parentheses. But sure enough, it still works, gives you negative 4. Okay. So now here, 16 to the 1/4 is saying there's some other number out there that when I multiply by itself 4 times, I end up with 16, right? So these are all the same number, and we're looking for what number would that be? Well, worst case, again, start back at the beginning. Try 1, 2, 3, 4 2s, for example. Oh, that gives me 16. So it would be 2. Right. The same thing here. This is saying what number times itself would give you 144, right? So we're only looking for 2 of them now. Again, worst case, you start back at the beginning, right? 2 times 2, no, right? 3 times 3, hopefully these you can do in your head. 9, 4 times 4, no. 5 times 5, no. 6 times 6, no. You can be here a while, blah, 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 blah. But eventually you'll see 12 times 12. Oh, sure enough, it's 144. So the number you're looking for here, what number times itself, only 2 of them gives you 144? It's 12. Right. So the key with that, the root and radical stuff there is normal power, right? Normal power, when you see that, is you're taking starting with this number. But a fractional power is a root or a radical. It's the same thing. It's asking, what would I start with to end at that number? Right? So keep that in mind as you're going through those.